Your task as scientist, researcher, student is to describe what happens. For example, you might be interested in how much gas do you burn or how much heat you generate. And that's your task. So you have to figure out how this happens. And this task is rather easy if the flow is quiescent, so it has just same speed every place, because if it has same speed every place, it becomes one-dimensional problem. And that's much easier to do. But in the case of these problems, which very generally are called turbulence, or spatiotemporal chaos, or many other words, it's a much harder thing. And why is it a harder thing? Because the state space is not what you as a human think, the configuration coordinate. State space is infinite dimensional. Or you can think of it, let's say, like Euler. There is some state of the flame. To specify it, I have to know the velocity at every point. But that's difficult. That's infinitely many numbers. So what I'll do, I'll produce a mesh. I pick a bunch of points, 1, 2, 3 to n, and I record the mean height or the mean velocity in each point. So I define ut as u of x. So at a particular point, I define this height. And now this becomes an n-dimensional problem. By discretizing it, I'm introducing errors. In practice, that's the only thing we can do on computers. I care about n equals infinity limit. So this very innocent problem is actually infinite dimensional. So the state space for this problem is the value at the first location, value at the second location, value at 64, 371th location, whatever your truncation is. And now, if I take a point here, that's unique state of the system. Up to resolution accuracy. And I have to make sure that this is representative of what I'm interested in. So to give you a sense, when we do this for Navier-Stokes fluid, what we do is we take a liter of fluid and we force it so it gets turbulent, but not very turbulent. It just, like in the ordinary plumbing, the things look complicated, but not having infinitely small vortices or anything like that. And then we require being, as you will understand later, we'll be interested in unstable structures, and they are exponentially unstable. So unless we can compute them very accurately, our computations are worthless. Accurate computations can be done, even though you're in these huge dimensions. So computer can actually rather accurately, if you start an initial profile of the gas, it can rather accurately, for a little while at least, predict the future. In this particular case, you realize that you should maybe choose your coordinates using something more intelligent than just putting little boxes in the space. And one of the intelligent things you can do is you can use symmetry. And I'll call this Fourier. There is no distinguished point on this burner. So if I look at it and then I turn it around, that's an equally good solution. That means my solutions are translationally invariant. I just relabel my coordinates. The physics doesn't change. So that's an example, totally simple example of symmetry. Whenever you have that, a natural basis is not using these boxes in space, but doing a transformation called Fourier transformation, which is what you see all the time in engineering and physics, because lots of problems that we care about assume translational or rotational invariance. We assume that space is isotropic or homogeneous. Whenever that happens, Fourier transformations are very useful. So instead of writing x at t point by point, you do a linear transformation on your basis set, and you rewrite it in terms of transform quantities. So replace spatial coordinate by sum of the waves. Let's run it. K of q, where K of q, that's just a boring scaling thing. It's probably 2 pi over L times K. And what you're doing is you're saying, this looks like waves to me, and waves are smooth. So I should be able to write it as a sum of something that looks like sine and cosine, and then something that wiggles twice and 3 times, etc. in this interval with some coefficients, which are called UK. And what you're using is you're using symmetry plus smoothness. So this problem naturally has solutions which are very smooth, because if something kinky happens, the gas will burn very fast there and even itself out. So typical behavior is smooth, and then a Fourier basis is a very natural representation. The state space representation is now U1. These are complex numbers, but in plotting them, you really need to do this in real numbers. So you write U of k, you write either as a pair of real numbers, or sometimes you want to write in a polar form, so the magnitude of the thing times a phase. And so you plot x1, x2, and now this thing goes from minus infinity to plus infinity. So again, you see that whenever you have an extended spatial system, it's infinite dimensional, because function needs infinitely many things to specify it. However, your intuition is that there will be no flame fronts that look like this, so that Fourier mode 2743 is going to be either not there or very small. There will be no very fine structure on this. You learn that instead of discretizing this way, there is a better theory for this set of problems, how to discretize them. It says I can write it as 0 to n plus small error, which is controllable. So these are two ways of starting with your problem and ending up with a state space. And you've done a tremendous abstraction leap doing this, because now what happens is, in the original problem, you had very good physical intuition what this is. You wrote the partial differential equation to explain that if there is some nonlinear term, some gradient, some Laplacian, you're penalized, and that's parameters in some way. And you can spend a few hours in the class, you can derive this equation, and everybody understands what this equation is. So this has a very deep physical meaning, and same is true of Navier-Stokes, Young-Mills, general relativity, all these nonlinear equations. It might take a semester to learn them, might take 3 days to learn them, but you understand them. So that makes sense. But to understand the behavior of the system, you have to make a mental leap to infinite dimension. Thinking even more, you might get to something that's much more abstract, which is you look at this, but you're representing that state, again, as a point. In this case, just linear transformations of the spatial coordinates.